Since somehow you found this video, I assume that you have seen the term automatic differentiation or Autodiff, and you're interested to know more about it and want to see whether it can help you in practice. It could be sensitivity calculation in financial engineering, or it could be finding gradients in machine learning. The purpose of this video is not trying to provide a strict mathematical definition of Autodiff, but we're rather going to follow a specific example step by step to see how the Autodiff method works. We will also walk you through a mini coding example for the implementation. So hopefully at the end of the video, we can understand the basic idea of Autodiff and get familiar with the available tools. Say we're given a function f that involves two scalar input and a single scalar output, and we're looking for the first order derivative. First, please allow me to abuse the notation a little bit using j of ab to denote the derivative at the point x1 equals a, x2 equals b. This is for simplicity and also serves as a reminder that Autodiff only solves for the numerical solutions instead of a closed form analytical solution. So first, let's warm up with something that we're more familiar with, which is the numerical approximation using the finite difference method. It is also called the bump and revalue approach, where we bump one of the input variables by a small amount delta, and then we get the difference in the output and divide it by delta. So one major drawback of this method is a truncation error, because we omitted the higher order tail of the Taylor series here. So the second drawback comes when we have thousands or millions of inputs and we need to iterate through this bump and revalue process for each of the input variables. That could be a huge cost. So this is where the automatic differentiation comes into play to tackle those challenges. In the next few slides, we will show how the Autodiff can give us accurate solutions with machine precision, and it can also reduce the computational cost by orders of magnitudes. To do that, we use the same example as before. We now look for the derivative of f with respect to a. So first, we reconstruct f as a composite function of all the elementary operations that involves a. So basically, we need to follow everywhere that we see a. So starting from the innermost layer, there is a sign a, which is denoted by the function h. And then the next elementary operation is multiplication by b, which is denoted by the function g. And then the last operation is addition of b squared. Now we can apply the chain rule to find the partial derivative with respect to a. And we can see that it's expanded to different levels of intermediate derivatives. And the final result becomes the multiplication of the partial derivative of w0 with respect to a, corresponding to the function h here. And then w1 with respect to w0, which is corresponding to the function g. And last but not least, the r with respect to w1. That's the function f here. So now we want to compute all these intermediate derivatives one by one. So naturally, we have two directions to do this. So from the innermost layer to the outer layer, or the other way around. And we name them the forward mode and the reverse mode. And then they can also be called a tangent mode or adjoint mode. So when we see tangent, just think of forward mode. And when we see adjoint, just think of the reverse mode. And we may have seen the term AAD floating around, and that is short for the adjoint Autodiff mode. And we will talk about that in a minute. Let's start with the forward mode, which is more intuitive and also conceptually simpler. To simplify the denotation here, we introduce a term called the tangent derivative, where we put a dot over the symbol. So it stands for the partial derivative of the symbol, in this case y, with respect to a chosen variable x, which is the underlying variable of interest. And this denominator does not change throughout the rest of the calculation. So let's see how it works using the same example. Say we're looking for the derivative with respect to a, then we choose x to be a, and that stays in the denominator. This is to say, no matter what the numerator is, we always have the same denominator. So here are some examples using this denotation. A dot stands for the derivative of a with respect to a, which gives 1. And b dot is the derivative of b with respect to a. And since these two variables are independent of each other, we have this value to be 0. And again, we always keep a in the denominator. So our goal is to find r dot, which is the derivative of r with respect to a. So this slide is where the magic happens, so you probably don't want to skip this one. Recall that we decomposed the function into elementary operations, or what we called the primal functions here. We follow the sequence to calculate the intermediate values step by step from W0, W1, W2, and eventually we get the scalar output R. And in parallel, we keep a record of the derivatives for each of the intermediate values with respect to A. You can pause the video here and give it a try yourself. It will be a good practice to refresh your first year calculus. So recall the seeding values of A dot and B dot, which is 1 and 0. Now we plug these values back into the formula to get our tangent values. And at the end, we get b times cosine A. As we can see, this is the exact same solution as if we manually derive this derivative. And this is why Autodiff can give us the exact solutions. So if we take a look back, we can see that the trick here is on the seeding. Say if we want to find out the derivative with respect to A, we plug in the seeds A dot equals 1 and all the other seeds to be 0. Similarly, if we want to find out the derivative with respect to B, we're going to use the seed B dot equals 1 and all the other seeds to be 0. So everything else stays the same, and eventually it will give us the derivative with respect to B. So in another word, we need to iterate through each of the input to get the first order derivative, which gives us a time complexity of O of n. This simply cannot cut it when it comes to thousands or millions of inputs. So this is where the reverse mode comes into play. Similar to the forward mode, we define the adjoint derivative. Instead of the denominator, we now fix the numerator with the chosen variable. That means y stays unchanged in the numerator. And we denote the adjoint derivative with a bar over its symbol. So for example, if we choose y to be r, then we use r in the numerator throughout the whole time. For example, r bar would be the derivative of r with respect to r, and that gives 1. And our goal here is to find a bar and b bar. And remember that r stays in the numerator. So now let's take a look at the adjoint computation. We still need to calculate the primal function as what we did in the forward mode. And what's different here in the reverse mode is that after the forward scan, we need to perform a reverse scan, starting from the last step all the way back to the first step to calculate the intermediate derivatives. And eventually, we're able to get both of the target derivatives, a bar and b bar, in just one scan. So now this is something. Say if we have 1,000 input variables, instead of iterating through all of these inputs for 1,000 times, we now only need to go through the function just once. And that's sufficient for us to get all the derivatives with respect to the underlying variables. So however, this convenience comes at a cost that we need to store all these intermediate values in a tape, because they will be used here and there in this reverse scan. To get a better idea of which mode to use in what kind of situation, let's take a step further to see how these two modes work for a function with higher dimension of input and output. Now we upgrade the function f to have 4 scalar input and 2 scalar output. So what do we do to find the Jacobian matrix using the forward mode? We're going to use the trick of seedings. So here we demonstrate this using a hand-waving way. So if we want to find out the derivative with respect to a, we need to set the seedings to a dot equals 1 and all the other seedings to be 0, and then perform a forward scan. And then we repeat that for each of these variables for a total of 4 times to get what we want. Things are a little bit different using the reverse mode because we plug in the seedings for the output variables instead of the input variables. And in this case, they are R0 and R1. So 2 scans will be sufficient to get all of the derivatives. So the first one would be on R0 and the second one on R1. And in practice, this may save the cost by orders of magnitudes when we have a huge amount of input variables and very few output data. For example, in machine learning, the output could be the value of a loss function and together with thousands of input coefficients to be trained. And in financial engineering, the output could be a single option price with all the market data as the inputs. So far, we probably can see that the adjoint autodiff, or AAD, is able to calculate the exact derivative at machine precision, and its cost is independent of the input dimension, whereas finite difference is a numerical method with truncation error and a complexity that grows linearly with the input dimension. So that being said, we can see that AAD would be most suitable for the cases where the input dimension is much higher than the output. As for the coding implementation of Autodiff, we can find a list of available tools at autodiff.org. There are different kinds of methods, and we only focus on the operator overloading method in this video. So this method introduces a new data type that includes an extra storage of the derivative of interest, and we can look at these values as a tuple of the original base value together with its derivative. And as its name suggests, the operator overloading method would overload the underlying operator to calculate the primal function and its derivative at the same time. And for example, sin x would be overloaded to calculate sin x, but also the derivative process as well. So in terms of programming languages, there are Python libraries available such as PyTorch and TensorFlow, and they're both well documented. And in this video, I'm going to walk you through a C++ example using a library called the DCO C++. We choose this C++ library because it better illustrates the two mechanisms of Autodiff here, and we'll see that in a minute. We're going to use the same function as mentioned before, and we denote the output using the vector y and the input using the vector x. So let's first take a look at the target function itself. The x vector is initialized, and then the function is called to perform this primal calculation, and then it's done. Then let's take a look at the finite difference method when calculating the derivative. So what we're going to do, we first bump one of the variables by a small amount of delta, and then we find out the difference and then divided that by the bump size, and then we're able to get an approximation of the derivative here. Now let's see what happens in Autodiff. As mentioned before, the DCO C++ library uses operator overloading method, which means that all of the elementary operators such as adding, subtracting, multiplying, and dividing will be overloaded by the library. And the variables will be using a new AD type. That's why we're introducing the template here. For example, in the forward mode, the tangent derivatives that are calculated in parallel with the primal function, they will be carried around by this new AD type. So at the end of the calculation, we can just simply extract that derivative from the output values. So to see this more clearly, we use a coding example here. we first define the new AD type under the tangent mode, and then we initialize the input and output vectors using this new AD type. And the next step is the key here. So we need to set the settings. We set the tangent derivatives to be 1 for that variable of interest, and all the other tangent derivatives will be 0 for the rest of the variables. And after that, we do the forward scan. At the end of the scan, we automatically get all the derivatives, and we just need to extract them from the output values. As we can see, they're all carried around by y here. On the other hand, the adjoint mode would need a bit more work because we need to perform an additional reverse scan at the end of the forward scan. So first, we define the new AD type under the adjoint mode, and then we initialize the input and output variables using this new AD type. And recall that we need to store the intermediate values for the adjoint calculations using a tape. So we need an extra step here to create the tape. And then we register the input variables on that tape so we know where to find them during the calculation. And then we perform the forward scan by calling the function itself. And also recall that in the adjoint mode, the seeding is done on the output variables. So first we register the output, and then we assign the seeding values to be 1 for the variable of interest. And then we're ready for the reverse scan. And right after that, we get the derivatives of all the input variables. So that wraps up the demonstration of coding implementation of Autodiff here. So the take-home message of this video is that the adjoint Autodiff, or AAD, can calculate the derivative to analytical accuracy, and its cost could be orders of magnitude lower in comparison to the finite difference method, and that is the case when the input dimension is much higher than that of the output. So more of the coding examples can be found in the website archquant.com if you need more details. And thanks for watching, and see you in the next video.